Okay, can you hear me now, Nelson? Okay.
Yeah, I can hear you now.
All right. Okay, I think we can start now. So close that. Go here. Okay, so we'll go ahead and get started. So today's going to be math heavy. We're going to, annoying. Let me see if I can turn off this left projector. On. Okay. Otherwise, there's a giant webcam of me and one big screen behind me. It's kind of weird. Okay, so today's going to be a little bit math heavy. We're going to start talking about mathematics for computer graphics, and I have over 45 slides, but we're probably not going to make it through most of them because I'd like to spread it out so we can kind of get some practice with it, as opposed to just talking your ear off and then it just kind of go in one ear and out the other. I've been on the other side before in the seat, and sometimes you do too much, or you think you can get through more than you can, and then you end up making it forgettable. So I wanted to kind of talk a lot. There's a lot of different areas we could talk about, and this list of topics here doesn't really begin to cover everything there is, but we can at least start to get a sense of what you can do with the 3D mathematics. And I also want to introduce you to a different kind of mathematics that you probably would never normally see in a university setting, and namely geometric algebra. Now, of course, the linear algebra is not a requirement for the course, so we're going to kind of go over some of those topics as we need them. I guess by just way of raising hands, how many people have worked with vectors or matrices in their math courses before? All right, most people. Everybody know how to do matrix multiplication? I give you a 4x4 matrix and said, multiply these two together. You feel pretty confident. You pull out a piece of paper. It's like, here you go, maybe. So we're going to kind of go over a little bit of that today. All right, let's see here. Before I go over that, though, I figured we'd talk about the homework a little bit. So let me move some of the stuff around. Close that. All right, so okay, so under homework. So here's homework 1. So so I have the link for the overleaf template over just like we did last weekend. So you submit your homework via the PDF, and then you basically do your work on GitHub, and then I'll pull your repository. I don't mind you putting executables inside your repository, but make sure that they're going to run on anybody's computer. So if there's any required DLLs or anything like that, make sure those are all in the same directory. So you may want to test that and make sure that it's going to just kind of run out of the box. Otherwise, it's going to count as the homework just doesn't work. So if I have no way of testing it, then it doesn't work. Okay, so let's take a look here at the description. Okay, so this is the second homework assignment, and it's primarily about 3D mathematics and game design. And there's all the grading criteria over here, so you know exactly what you need to do. I'm generally kind of all half or nothing. So if you, for example, write a sentence for the design paragraph, I'm going to say half because it's not a paragraph. Give me a paragraph, then you get your full points to it. So pretty easy, just you fill it in. And generally, these things are just your way of restating either what the homework problem is or what happened while you did the homework, okay? As a help, I have put some LaTeX code that would be useful for doing a matrix or that kind of mathematical type stuff. So you can use this as a template to kind of figure out how do I typeset this mathematically. And it's pretty simple. And there's two sets, just in case you're trying to figure out how do I do cosines or Greek letters or anything like that, and you get a sense for this. Another thing you can do is if you're on Wikipedia, and say you're looking at like quaternions or something, and you're like, wow, they have some really awesome, they have a really awesome formula I can start out with, right? Like say this one. This kind of gets you a head start. Well, if you go to like edit source, you'll notice that they actually, inside these math, kind of like HTML stuff, but this is all LaTeX code. So you can just take this LaTeX code in here and copy and paste it. So if you're looking for an idea, how do I display this formula, or they kind of got this formula spot on for what I needed to do, then, just go in there and that'll get you where you need to be. All right. Okay, so basically we're just, for the questions, I just want to get a feel for your ability. So I wanted to do a 3x3 matrix multiplication. So take the letters and scramble them up. So don't do A, B, C, D, E, F, G, make your own mix and then multiply those and do that arithmetic there. And then we're going to go over this today. How do you do the inverse of, say, a rotation matrix? Talking about vector dot products, what information, the most important piece of information from a dot product, as far as we're concerned. And then what's the product of a 4x4 matrix and a vector of this type? This is very important for transformations. Like, how do you actually rotate points in 3D space? This is a critical part of that. And then the main requirement is to do the 1 hour game jam. So last week was pizza. So if you want to do pizza again, you can do pizza, or do the one that's actually on Saturday and challenge yourself to actually complete that one. Okay. And then the additional requirements, if you're undergrad, then you pick two of them, or one of them, you pick one of them. And if you're a graduate student, then you pick two of them. Okay. So your choice. And there's three that I put in there. So the first is whatever 3D engine you picked, figure out how you use the vector and matrix operations. So pick 3 different kinds of operations that you can do, test them out, write some code to test that out. And then requirement number 2 is to calculate matrix transformations. So, for example, calculate an X rotation and make sure, say, the inverse of the matrix actually, when you multiply against the original, gives you the identity, which is a fundamental identity for matrix inverses. Or lastly, use a 3D engine that you picked to modify a 3D transformation in some kind of way. For example, moving a player around the level or rotating an object. Okay, so we want to get some experience using these mathematical tools. Okay, and that's basically it. So this shouldn't be too bad. And this is due on Sunday night. Okay. And if you have any questions, feel free to come talk with me. And it's better to get help early than to be struggling at the last minute, because it's not a good position to be in. Okay. All right. Any questions or comments on homework 0? All right, I'll take the silence to be unwavering applause. And okay, so let's start doing some math. So I figured this is like a set of slides I'm still working on, trying to make it better and better over time. But I figure I'd start with what I'm calling a gentle introduction. Okay, some of the like most important pieces of information. So I figure we could start with some two-dimensional math. Okay, something you could work out on a piece of paper. And for two-dimensional math, you might have a vector with two components, x and y. All right, the first component and the second component. And so one of the first things you need to do is, well, how do you add and subtract vectors like this? Like you have a set of numbers. What do you just add them component-wise? Do you add them together into one giant sum? You know, there's essentially rules to how arithmetic works when you were talking about higher math. So if you guess that you would add component-wise, that is correct. So you'd add the x's together and you'd add the y's together, or you'd subtract the x's and subtract the y's, and they stay in their own slot. In the same way that if you're working with a spreadsheet, you know, it doesn't all collapse down to one element, but some of these mathematical operations will do that, okay? So that's one of the first things we need to figure out. How do you add and subtract points, right? So one key thing you might want to do is move a player around the screen. That would require you to add some kind of delta position to the original position in order to move around, okay? It gets more tricky when you're talking about multiplication, okay? Because there's more than one way to multiply. And not seen on this slide just for space is scalar multiplication. In other words, how do you know, can you multiply a scalar number? In other words, a number with just one component to make the numbers bigger or larger, okay? So we have, for multiplication though, we have two particular kinds that we're interested in. One is called the dot product, and the other one's called the cross product. Anybody familiar with the dot product? What does that one do? Dot product. Gives us a scalar. Okay, that's good. The scalar we get is we just multiply pairwise, so ax times bx plus ay times by. All right, and it's not immediately obvious what that gives you, but there are certain conditions where you can. It's related to the cosine of the angle between the two vectors. So if you have two vectors a and b, the cosine is what the dot product encodes in it. Okay, and we'll take a look at that in just a moment. And then we have the cross product. If you've anybody who's done a determinant in math before, okay, so you know that if you had a matrix A, B, C, D, then you do A times D minus B times C. And if you were to arrange the A vector and the B vector in a matrix, you would notice that this actually is the same calculation in two dimensions. It's just the determinant of a 2x2 matrix, although we will see as you get higher orders like 3 dimensions and so on, that doesn't remain the case. We get 3 components. So in this case, it's 2 dimensions and we get 1 component. In 3 dimensions, we get 3 components. And then typically your math teacher will say there's no such thing as a 4th dimensional cross product. And that is true. However, that doesn't mean you can't do the same thing. That just requires a different branch of mathematics called geometric algebra, which we're going to talk about a little bit later. Okay, so we have some tools. We can add and subtract vectors together. We can multiply them together and get the dot product, so we can find out what the cosine of the 2 angles are between the 2 vectors. We can scale it, so we can make the vectors bigger or smaller. This would be useful if you had a sprite on the screen, you want to make it bigger or smaller, you can scale it, just multiply those. And then a question we have not answered is, well, how do you move or rotate a point? That's a little bit different story. All right. So moving on from there, okay, we have a few tools we'd like to do. We have not answered one of the questions. How do you move or rotate this? Before we get to that one, I wanted to just kind of expound on the cross product here. So Can anybody guess what special value that is encoded into the cross product? What do you think? Area. You are correct on that. Okay. Let's see here. I don't know if I can easily draw on the screen. Maybe I can. Let's try it. Yeah. So if you had a vector, cool, that works. Let's say that's A and B. Okay. If you were to take the cross product, you can basically say, let's add the B vector there and add the A vector there, and the cross product will give you the area of this parallelogram. Okay. It also works in 3 dimensions as well. It gives you the volume of the parallelepiped, you know, as you extend it into 3 dimensions. We're doing too much for this system. It's breaking down. Okay. All right, so let's erase that. The other thing, though, that it's encoding is the sine function. So the dot product encodes the cosine, the cross product encodes the sine. Although it's far easier to get the sine of a function from the dot product. But what would we have to do that? How do we get a sine, the value of a sine, if we only have the cosine? You could do that. There's another easier way of doing that. Maybe a special identity you may have learned about. You have cosine squared theta plus sine squared theta equals 1. So we know the cosine, so we could just solve the equation for the sine. So you have sine theta equals the square root of 1 minus cosine squared theta. So that would be another way of getting the sine without having to go through the getting the cross product. I got to do something about this blanking out here. Let's see here. Maybe it's getting confused trying to do my video. Let me try to stop the video there. Stop the video here. This might be doing better. We'll ask Nelson, is the screen going black and switching between black and the slides?
No, it's fine.
Okay. So it's just here that we're having issues. Okay, so let's go on. Let's explore this. You know, has anybody ever wondered where these things come from, though? Like, who comes up with things like cross products and dot products? You know, you have a math teacher who goes up on the board, he says, this is what the dot product is, and this is what the cross product is. And then you're like, well, where'd you come up with that? These are questions I always seem to have in my mind. I was like, I wasn't content to have no for answers, so I actually went and figured it out. And so, ironically, it's pretty easy. I think you could teach a high school student the concept behind here. So, so we all know about the distributive property. Okay, I need to fix that. That should be AX plus AY. And this should be BX plus BY up over here in this area. This should be B. Oops. Okay. But it all comes from we come up with some rules. So we come up with these things called basis vectors. Okay. So we might say E1 represents the X direction and E2 equals the Y direction. Okay. So it's clear to say that this, you know, A vector, AX and AY, this is the same thing as just saying it's a vector AX and AY with the different components. Okay, but what we can do is we can multiply them just as if we were doing algebra. All right, so for example, we could just use a distributive. So AX E1 times BX E1, AX E1 times BY E2. And we just do this just like you were doing this distribution in your Algebra 1 class. And we have some special ways of making the notation nice. For example, if we have two E's like EI and EJ and we multiply them together, then we just put the numbers together, okay? That's for 1, 1 here, and 1, 2, and 2, 1, and 2, 2. And then we could also say that if we flip the direction, okay, then it becomes reversed. This is kind of like right-hand rule and left-hand rule, okay? So if you put your fingers this way, then your Z direction points one way, but if you do it with the other hand, then it's the other direction. So if we rewrite this, you'll notice, and then we start to combine terms, then you'll notice that over here we get the dot product, and over here we get the cross product. And so there is a way that the math just kind of works itself out, and this is where these things come from. In fact, before we had this notation of dot product and cross product, they were already kind of working on this higher dimensional math in the 19th century, and coming up with new different kinds of algebras. All right, quaternions is an example of that, and we'll talk about those in a little bit. So last week we were talking about this idea of divide by Z. Okay, so we want to, now that we know how to kind of work with our vectors a little bit, we'd like to take those vectors or points in space and figure out, well, how are they supposed to look on a screen? Okay, so I went ahead and I grabbed a few points here. I just kind of made this up. Oops. So we had a box going from -2. This is X, Y, Z. So -2, -2, +2 in the Z direction. So over here, this point, all the way to this corner over here, 2, 2, and 4. So I put it out there. So you can figure out the rest of the coordinates of the box just simply by combining all the combinations there. Okay, and so if we were to divide by Z, then, for example, this first coordinate, -2 divided by 2, would just be -1 and -1, and the other coordinate over there would be 1/2 and 1/2. So all I've done here is just plotted those points onto the two-dimensional chart here. That's all I did. In fact, what I did was I went to Excel and I made a little tool to so I could put any set of points that I wanted to, and then it would just do this calculation for me. And so you can see that by dividing by Z on this two-dimensional shape, the 3D shape just appears. It's not like anything crazy going on. Anybody done any perspective drawings? Like one point perspective? No? Anybody ever heard of this? No? Okay. Let's see here. Let me see if I can. I hit. Okay, I'll try the annotation tool again. Okay, so the idea is that if you just had a blank piece of paper, you could draw the horizon, just a straight line across the horizon. So let's try that. Draw a straight line. That works. And if we were to use the center of the screen, you'll notice that all these points project to a certain spot. So I'm just grabbing these lines. Okay, they all just kind of go to one spot on the screen. And the same concept here. If I were to draw lines, you'll notice that that line's a little off, but you'll notice that there's one area. So if you put like one point on your pencil and just go to YouTube and search for perspective drawings, and you'll see that you could just put one spot on your paper, and then no matter how you draw your lines, as long as they're parallel, they're all going to kind of go towards that one point, and that's how you get your 3D perspective. Okay, it's actually pretty easy to do that. All right. Okay, let's clear all drawings. Okay. So pretty easy. So dividing by z. So at some point in our 3D graphics pipeline, we're going to have to come to this point where we project our points. However, I mean, it is easy. This is pretty straightforward. If you want to make a very simple graphics engine, you can more or less skip all the extra details around it. But anytime you want to get more general, like, you know, what if you wanted to pretend you're making a Panavision camera or something? Then you really have to start dividing your pipeline so that you can accommodate things like that. Okay, so that's kind of the gentle introduction. Anybody have any questions? Okay. Okay, so let's continue talking about vectors. All right, and a vector represents a quantity with both magnitude and direction. Okay, so a vector has a length associated with it. It also has a direction associated with it. We could consider it an array of numbers in a vector space. We'll talk about vector space in just a little bit. And we might just say it's just a collection of points, say x, y, z. All right, so if it was a one-dimensional vector, it would just more or less tell you where you are on the number line. Okay, so are you pointing to minus infinity, you're pointing to positive infinity. And then the magnitude would just be how far are you along the number line. 2 dimensions, we're extending the concept to a plane. So we'd like to figure out, you know, imagine a circle and a vector would be pointing in any one of the directions. And in 3D, we have a volume. So we're, you know, the space that we live in is what you're no longer confined to just moving forward, backward, left, and right. You go up and down. So in reference to the previous slide, though, for projection, it is, and other transformations, it is helpful if we add an extra coordinate. And we'll call this coordinate W, but it allows us to represent vectors and points. Okay, because a vector represents magnitude and direction, whereas a point, we actually expect it doesn't really represent magnitude or direction, or represents a position, okay? And the projection part, though, is if we wanted to go from 4 dimensions to 3 dimensions, it works the same way as if we're going from 3 dimensions to 2 dimensions. We divide by that last component. So if we wanted to, we can see a vector, you know, you don't divide by 0. So that's convenient. So you can see that concept does not really represent it there. But a point does, because if you divide by 1, you still get your original point out. Okay, so there's a difference there. But the other importance being, we're going to be using 4x4 matrices, and you cannot multiply a 4x4 matrix by a 3x1 matrix. You just cannot do that. You need a corresponding number. So if you're using a 4x4 matrix and that last component is 0, then we still get we ignore any kind of translational component to the whole deal. Okay, so some more vector operations. It's helpful to know what the length is. So this is more or less an application of Pythagoras' theorem. And you can just say, you just take the square of each of the components. So say ax squared plus ay squared plus az squared. And then you take the square root, okay? And in a similar way, I don't remember if I mentioned the norm, but you can make a vector a length of 1 if you just simply divide by the length. Okay, so if you have a vector and you want to normalize it, you would just divide by the magnitude of the vector. And now your vector will have a length of 1. So here's the dot product, and this is why that normalization becomes important. So here's the three-dimensional dot product. We just multiply pairwise ax, bx, ay, by, az, bz. And you'll see over here that it's equal to the magnitude of a times the magnitude of b times the cosine of theta. So because of that, if the magnitudes of a and the magnitudes of b are both 1, in other words, they're both unit vectors, then if you take the dot product of a and b, what are you going to get? If a and b are both normalized vectors, in other words, they have a length of 1, then what is the dot product of a and b? Cosine theta, because it's the magnitude of a and magnitude of b goes away. You still get the cosine. So if you wanted to measure for example, let's say you want to find out what direction you're looking in. So you know what direction is up, right? So you take the direction you're currently looking at, and you can take the dot product between up, which is 0, 1, 0, if y is going up, and your current position, and now you know, oh yeah, you could take the arc cosine and figure out, yeah, I'm pointed 45 degrees up into the air. Or you could figure out if two tanks are traveling on a field, what direction should I turn, or should I make my new, which way should I be turning? Then you can use this relationship to find out that angle. All right. And now we come to the cross product. This is a little trickier. We'll see how we can get these numbers with the geometric algebra as we kind of continue today. But you'll notice here a quick trick that I use is to remember this formula is you start with the first is you're starting out with x and then y and then z. So because I'm starting off with x, then I'll start with y. I go with y and then z. So I know it's ay times bz minus the opposite, okay, z and y. Now the next component is is y. And so I need to go to the next letter after y, it's z. So we have az, and then we wrap around times bx minus ax times bz. And then lastly, we're starting off with z, so I go back to the beginning, and then we have ax times by. All right, so that's my handy trick. Otherwise, you might make the mistake of getting the middle one backwards. In other words, it's not ax times bz, it's az bx minus. So you get the opposite sign. It'd be the wrong thing. But if you were to take the cross product, you get the magnitude of a times the magnitude of b times n times sine of theta. Now, n is the vector. Can you guess what direction it's going to point in? It's going to point perpendicular to a and b. Okay, so if you had two vectors, and if you could just imagine them on a plane, then the two vectors are going to point perpendicular to a and b. Okay, and that's the angle of rotation. So if you're using right-hand rule, you might have to think curl, like which direction are you curling around. But if you've ever maybe you take physics class or something, and you're using right-hand rule, and so this is the y-axis with your index finger, and then you take the x-axis with your thumb, and then you point your fingers perpendicular. Okay, then that is the axis that you would get with the cross product. Okay, so that's right-hand rule, and then if you do it the other way around, then it's left-hand rule. So you'll notice that that B cross A is not the same thing as A cross B. Okay, in fact, what you end up getting is the opposite direction. Okay, simply because of that. So that's what that n vector represents. N represents the vector that is perpendicular, or we would call it orthogonal to A and B. So if A and B are both unit vectors, then what's going to happen to this n vector? Is that also going to be unit length as well? And the answer to that one is yes, it will still be unit length. All right, so if you take the cross product between any two unit length vectors, then you still get a unit length vector out. So this is very handy if you're trying to figure out what direction should I rotate around. If I'm trying to go, say, maybe I have two directions and I'd like to rotate around an axis that's perpendicular to both of them. So I'm kind of twisting in the right direction, then that would be a useful tool for that one. Another useful tool is if you want to find out what the geometric normal of a face is. In other words, we have these, like, we're all sitting in front of tables that are pretty flat, or, and we're trying to figure out, I'd like to shade this in three-dimensional graphics. This is where you need the dot product and the cross product. So the cross product is going to give you the vector, the normal to the table. So you take two sets of points and find out those vectors. Then you take the cross product that gets you the direction pointing straight up. And now you can use the dot product to figure out, well, how bright should that table surface be? Because you'll take the vector of the light and the normal of the surface, and you'll take the dot product between those two, and that'll tell you exactly, that's Lambert's law, and it gives you cosine, and that's going to tell you how bright your table should be, okay? These are very essential tools, and we'll see more of these in practice, but these are indispensable tools. You have to just know how they work. So we spend some time kind of concentrating on them, okay? So it is very handy if you were using a vector library. You should be able to figure out what's the length of a vector, what's the dot product of two vectors, what's the cross product between two vectors, what's the norm of a vector, where you take it could be any length, but then you divide by the actual length to get a unit vector out, okay? So those are all very important operations. So let's talk about space real quick. So we talked about vectors. That's our sense of how are we pointing in space, right? And but we need to have like some way of measuring. Okay, so we're all pretty much familiar with Euclidean space, r squared. So you have the real numbers, right? So real numbers in 2 dimensions, real numbers in 3 dimensions, right? We use this power notation to kind of describe Euclidean space, all right? Well, the Euclidean space kind of starts running out after about 3 dimensions. And then you have to wonder what if the math still works if you keep going. Like if you go to 4 dimensions, does it work? And this is where I feel the Greeks stopped in the thinking. Like they kind of focused on what you can see. And the last couple of centuries we focused on, well, we know that the reality is more than just 3 dimensions. We have a 4th dimension that we know that time is, so we have space time, it's all integrated together. So we have this, what's called Hilbert space, and this extends this concept to n dimensions or even infinite numbers of dimensions. We can actually have vectors in the same way that you have vectors that are orthogonal to, on a plane or in 3D space. Now you kind of have to, your imagination switches off, because can anybody imagine a vector that's perpendicular to 3 vectors that are already perpendicular? Like if somebody said, here's a cube, a Rubik's cube. Now imagine a vector that's perpendicular to all 3 of those at the same time. And I think my imagination starts shutting off at that point. I just cannot imagine. I mean, I understand the concept, right? You have the number line, that's 1 dimension. Then you add another one, that's 2 dimensions. Then you add another one, that's 3 dimensions. And theoretically, when you throw a 4x1 matrix, you have X, Y, Z, W, technically, yeah, there is your 4th dimension, and it's completely independent of the other 3. And so, yes, the math still works, okay? So that's what Hilbert space is. And the whole idea here is that we use collections of numbers to specify a spatial position. So, but The other thing, though, is that, we think of space as orthogonal. In other words, you have your x-axis, your y-axis, and your z-axis, but it doesn't have to be that way, okay? You can have three axes, and as long as they just intersect at one point, they could be skewed, okay? And so they don't necessarily have to be orthogonal to each other. So when we say orthogonal, we mean they're all at right angles to each other, okay? All right, so and you've kind of worked with systems like this before. When you try to solve systems of equations in more than one variable, they're not necessarily at right angles to each other. They could be, represent a different kind of function. Okay, but if you do say orthogonal, it means that the axes are perpendicular. So let's go with, we looked at this a little bit, the standard basis. Okay, so we have these basis vectors. I bet most of you have never seen the E notation, but you probably have seen I, J, and K. All right, everybody's seen I, J, and K before? Okay, you may have seen I in terms of complex numbers. That is all connected to the same thing, okay? So, if we have a vector, say V, Vx, Vy, Vz, then we can represent that as a linear combination of the real values Vx, Vy, Vz with these basis vectors. And that makes sense. If we look at these vectors, we can tell that they're orthogonal to each other, because if you take the dot product between any two of them, right? So like if we take the dot product of E1 and E2, we can see that 1 times 0 is 0, and 0 times 1 is 0, and 0 times 0 is 0, and you add them all together up and you get 0, okay? That shows you that they're orthogonal to each other, because you get that 0 result. And that's just kind of how they're based, okay? And so if you were to generalize this to n dimensions, then we'd say EI is a vector with 1 in the ith coordinate with zeros elsewhere, okay? So this kind of goes, it can go as much as you want. And we're going to see how that works here, okay? So now that we have like this idea of a space, okay, we do need to kind of understand a transformation, okay, because we are basically, we want to go from one space to another, all right, one space to another. So in our 3D graphics, right, we have a couple of transformations that we need to understand. So the first is called a linear transformation. And a linear transformation, this is something you'd learn in linear algebra, but it preserves vector addition and scalar multiplication. So if you were to wanted to prove that a certain kind of algebra is linear, then you'd say, well, if you had, and notice this is bold-faced letters for F and bold-faced letters for X and Y. It means that they're functions on vectors, and X and Y are vectors. So if you were to have a function, F, operating on X and Y, if it's a linear transform, then if you could just add X and Y together and then do the function afterwards, okay? So it doesn't matter whether you add them first or after, the function still works the same. And then two, if you were going to scale that function by, say, constant K, then you could just as well do that scale first on your vector, but then do the function. All right, so this idea of a linear transform means that this certain kind of operation is preserved. All right. So then we have another kind of transformation called an affine transformation. All right. And this is a kind of transformation that performs a linear transform and then a translation. Okay. So it changes changes your coordinate and then it moves it around. That's another way of thinking about it. We're going to see how that works in a little bit. But what it does is it preserves parallelism of lines. Okay, so if you had lines that were parallel, they remain parallel. So can anybody, if we go back here a couple of slides, can anybody guess whether, because there's matrices that do this particular thing, is this an affine transformation? Think about how we started out, right? Where we have a box, we have two cubes or two rectangular boxes. Would this be an example of an affine transformation? No. Well, why do you say no? In some cases, but what about these lines over here? This line and this line. What about the lines going into the distance? Those aren't parallel anymore. They used to be parallel because it's a box, but now they're not parallel anymore. So we would not say that's an affine transformation. Maybe in some cases it is, right? Where they're all on the same plane, you know, perpendicular to where the axis of, or where the projection is going to. So it's not really affine. And we can kind of just say, well, no, it's not, because it doesn't preserve the, preserve the parallelness, okay? Okay. Although it can mess with your lengths or angles, all right? So it can warp it and do that kind of stuff, okay? And then an orthogonal matrix means that its inverse is the transpose, all right? And we'll talk about that in just a moment. Okay, so I just wanted to list a few of these different kinds. All right, and we're going to get into more detail later. But the first one is the translation matrix. This one just simply moves a point around in space. It just takes the points and moves it around. So would we call this, what do you think? Would this be an affine transformation? We just add a constant value to all the XYZ values. So yes, this would be an affine transformation, because, you know, if you had, I don't know, I'll just use this eraser. Okay. So if we just have this eraser and we just say we're going to move it, and we changed whether the parallelism of the lines in the object, they all point the same way, right? I didn't twist it so it's now bending or something. Okay. How about rotation? What do you think about rotation? Yes. So the answer is no for translation. But that's because the transpose is not the inverse. So in other words, if I were to take translation matrix and I moved it, the inverse would have to be, I'd have to subtract what I added, okay? Whereas a transpose just means you moved elements around, basically flipped the matrix on its diagonal, okay? But that's not happening, okay? So let's go to rotation, okay? And so sometimes we'll use like Rx theta to represent a x-axis rotation, or Ry to represent a y-axis rotation, or Rz to represent a z-axis rotation, okay? It doesn't necessarily, although there's another way of doing that, where you can just say, well, I want to rotate along a certain axis. But let's talk about rotation. So if I just rotate this object, is that an affine transformation? Yes, because the parallelism of the lines, okay? And in fact, the lengths and angles are also preserved as well. Is it an orthogonal matrix? Now, I don't expect you to just answer that because we haven't really proven that, but it is. A rotation matrix is orthogonal. You can take the transpose of a rotation matrix. That is its inverse, all right? So then we have a scaling matrix. So we take this eraser and we'll like make it bigger, all right? Is that an affine transformation? It is an affine transformation. Okay. It doesn't necessarily have to be orthogonal though, right? Because you could say, well, I want to squish it, you know, maybe you want to squish it down. You're doing some kind of squash and stretch animation. That preserves parallelism of the lines, but not necessarily lengths or angles. So unless it's a uniform scale, that is not going to be necessarily preserved, okay? And then we have a shearing matrix, which I'd like to do some more of these next week. So I'm not going to get too much in some of these. But it'd be nice to see what they do. Like you hear a shearing matrix, you're like, well, what does it do? Okay. Some of these you avoid in computer graphics because then they make it very difficult to find the inverse of a matrix. You basically have to like actually calculate the inverse, and not with like an easy way like the orthogonal matrix approach. Okay. We have this next one called E, which is an orientation matrix. So it incorporates the op, pitch, and roll. All right. And we'll probably talk a little bit more about that one next week because you get some certain issues that go along with it, like gimbal lock, where it becomes impossible for you to like just say, you know, do the X rotation first, then the Y rotation, then the Z rotation without something getting all messed up in there. Okay. And then we have parallel projection and perspective projection. Okay. So let's talk a little bit more about geometric algebra, okay? And we showed a little bit of example in 2 dimensions how you might use these basis vectors to get the dot and the cross product. And this is these are very interesting. This is something I got introduced to in 2012, and it's a very fascinating, I guess, excursion to mathematics that I'd never, you know, had never even thought about. But it's actually really, really amazing. So you have these products called the wedge product and the anti-wedge product, okay? And Grassmann, just to kind of give you some historical context, Grassmann is a mathematician who lived in the 19th century, and he kind of developed this algebra system, and he used a little bit slightly different terms, but it was basically to handle these vector kind of operations, okay? And so we have some shorthand notation we looked at earlier. So if you were to say EI, wedge, EJ, then you could just slap them together. So EIJ, and they're anti-commutative. In other words, if you flip the direction, then you get a negative sign, right? So if you had E12 and you wanted to, and you had an E21, you can put them together, but you just have to remember to reverse the sign on the one of them, okay? And if you remember from math, you have this, when you're talking about imaginary numbers, and you have I, and they said, well, if you take I squared, you get -1, right? So you can't take the square root of it because it's, you know, it's undefined, okay? Well, the whole idea here is, what if you just change the rule? Like, what if you said, if you had 2 of these basis vectors and you took the wedge product between the 2 of them, what happens if it was 0? You know, like that term just disappears, okay? Or what if you did it the other way around? You had 2 orthogonal basis vectors and that product is 0. What happens? Like, what if you just decide to try this out? So let's try it out. So let's start with the first one, the wedge product. So we'll just say anytime we get 2 E's together and they're the same value, then we'll keep it as 1. And if they're orthogonal to each other, we'll say it's 0. Okay? So just like we showed before with 2 dimensions, let's do this in 3 dimensions. And so we can say A wedge B, and we just use the associative rule or distributive rule, right? So we can see that we have AX E1 times BX E1, so we'll get that. And then with AX E1 times BY E2, and we're just combining terms here just to kind of shorten it up. And AX E1 times BZ E3. And so now we have, you know, we just keep doing that. And now you notice we have a few terms, like we have E12 here and E21, okay? But we said that the rule here is that if they're different, then it's gone, all right? So all that's left, if you look, is AXBX plus AYBY plus AZBZ, okay? And with some very simple algebra, we basically said, okay, well, that's how you do the dot product in 3 dimensions. And you'll notice that it went from a 3-dimensional number down to a 1-dimensional number, okay? And in fact, maybe another way of thinking about it, it just went to a scalar value. It's not even, it's a dimensionless number. It's not even associated with a vector at all. Okay, so that's the wedge product. And so now we have, let's look at the anti-wedge product. And we could say, well, let's do this the other way. So we'll say that EII equals 0. So we'll just make those terms go away. And we'll say that if we needed to switch the order of an IJ to JI, then we just flip the sign, okay? And so what happens here is if we do the exact same math, so all this is the exact same as the previous slide over here, but now we're going to combine terms. So we'll group them up. So we'll have like AXBY times E12, because we're getting rid of the E11 term and the E22 term and the E33 term. And so now we have 6 groups of numbers here. So E12, E13, E21, E23, E31, and E32. And we'll just flip those around so then we can combine everything all together. Okay, and you'll notice over here that if we organize them, say like over here, we're just missing the 1, the 2, and the 3. So we have a different kind of vector here. And you'll notice though, this is the same thing as the cross product in 3 dimensions. Okay, just like we showed for the 2-dimensional case a little while ago. Okay, but you notice that this is what we would think of as the x-axis, the y-axis, and the z-axis, but this is not the same thing anymore. This is what you might call the dual. Okay, imagine we live in reality. But if you were to kind of like flip it on, there's like an alternate reality, represents like everything else. And in math, sometimes you get this concept called a dual, where it's like, okay, this is the number on the other side of E1. This is the number on the other side. And so this is not really a vector, but it's a bivector. And if you were ever wondering, why does the cross product act weird? Like when you look at it, and you say, well, if you multiply B cross A, it's not the same as A cross A, it's flipped the other direction. And not only that, is it has this idea of an axis of rotation around it. It's a very weird concept if you think about it. This just doesn't make sense, okay? And because of that reason, we can see here clearly why it's not the same thing as a regular vector, okay? But what's cool about this is you can, if you want to, you can work it on paper and do, well, does this work now for 4 dimensions? What if I had 4 dimensions like E4? And you can actually do all this math, and now you have come up with the 4th dimensional version of a cross product, which is pretty cool because generally you kind of go through school thinking they don't exist, and they don't exist in the normal sense, but there is a way to get them. And this is how you get them. In that case, what ends up happening is you have you have your vector, and then you go to then you get a trivector, a bivector, and then a quad vector. Okay, and we'll see that in just a bit, I think. I don't know if I did that or not. Yep, I did. I did not do that. So I didn't want to like make this too in depth, but it is very cool. So this geometric algebra, there's actually really nice properties associated with it. And I hope to expose you to a little bit more of that as we talk about this in class. But it's a really cool concept. Where do you get these products from? Okay, so let's go back to matrices. All right. So generally, when we're talking 3D graphics, we're concerned with 2x2, 3x3, and 4x4 matrices. Although in some special cases, we might care about 2x3 or 2x4 matrices or so on. But generally, we ignore the 2x2 matrix case, and we just care about 3x3 matrices and 4x4. And the reason for that is that a 3x3 matrix would represent a rotation 3D space, and a 4-dimensional a 4x4 matrix will allow us to represent a rotation and a translation in our 3-dimensional space. Any questions so far? Okay. So let's take a look at some of the different things that we can do with the matrix. Okay, we looked at vector operations like the dot product, the length, cross product, and so on. So one of the first ones we'd like to be able to do is the transpose. Okay, so if we take the transpose, we basically just flip along the diagonal going from the top left to the bottom right. So you'll notice C over here is now down here, and you notice B over here is swap spots with D. Okay, so the transpose is actually a very simple operation to apply. Okay, and we talked about an orthogonal matrix being a certain kind of matrix that if you were to do the transpose, it's also the same thing as the inverse. So in order to find out if you can even do an inverse, though, you have to be able to take the determinant. And the determinant, this is for the 3 by 3 matrix above, is you basically can recursively apply an algorithm to find the determinant of the next smaller submatrix. Okay, so in this case, here's a 3 by 3 matrix worked out, and down here you can see, like, say EF HI. That would be, you take the diagonal, so E times I minus F times H, B times I minus F times G, E times H minus E times G, and then you take A, which is at the top here, times this matrix down here, B times this other matrix down here, and you add it together and you get a scalar number out. Okay, so if the determinant is 0, you cannot take an inverse for the matrix. Okay, so that right there is a very important thing to know. If you take the determinant of a matrix and it's 0, you don't have an inverse, and that tells you that at least 2 columns are linearly dependent on each other. In other words, they're basically the same exact equation, and they're parallel with each other. Okay. If the determinant is not 0, then you know that all 3 of them are linearly independent. Okay, so if you were solving an equation in 3 unknowns, you'd have a 3 by 3 matrix associated with all the coefficients of your 3 unknowns. And if you take the determinant, then you can figure out if you're going to be successful in finding the answer for your X, Y, and Z. Okay, so here's a rule. If you happen to know what the inverse matrix is of, say, A, and you take the product of them, A times A inverse, then you end up getting the identity matrix. Now, can anybody tell me what the identity matrix is? Identity matrix. Yes. Okay. So if A here was a identity matrix, A, E, and I would all be 1, and everything else is zeros. Okay. So it's very easy to find an identity matrix. All right. And if you have an inverse, then A times A inverse equals I. In other words, the determinant's not 0. And that's pretty good, because now you know how to get the identity matrix back. Okay, so that's one way of testing to see whether or not you come up with an inverse matrix algorithm. That's one way of testing. If you were writing like a unit test for your inverse matrix, we'd probably test to make sure the determinant's not 0 and that you get the identity matrix out. Now, as we mentioned earlier, if you take the transpose of an orthonormal matrix, then the determinant is plus or minus 1. So the transpose is the inverse. Okay, and this is there's a homework question that asks you to prove it for a rotation matrix, and which is pretty simple, because then you just multiply. You'll be multiplying cosines and sines together, so you'll be able to use your trig identities to figure out whether or not that's actually true or not. Okay, so in order to multiply 2 matrices together, we basically take the row of the first matrix and multiply it with the columns of the second matrix. Okay, they're generally non-commutative. So if you have A times B, it's not the same thing as B times A. It's very rare for that to happen. So don't assume that you can just swap the order of multiplications. And we'll see where that kind of comes in handy when we're talking about transforming matrices together. Okay, so when you multiply, you take the row I of matrix A and multiply it by column J of B, and you basically do the dot product between them, okay? So if you look over here, you have A, B, and C times J, M, and, oops, went too far forward, J, M, and P, okay? So it's like taking the dot product for each one of these, okay? And then matrix operations end up concatenating right to left. Okay, so when you're looking at when we're talking about 3D transformations in this class, and I know it's technically different if you're talking about left hand versus right hand, but we're going to stick to this one particular way of doing matrix math so we don't get confused, all right? And so in other words, if you had a bunch of like a rotation and a translation and a scale, you just work your way right to left and you'll know exactly what's going to happen. So you'll see that we scale first, then we rotate the object, and then we move it around, okay? And that's how you should think about it. They work right to left, very important, okay? So if you have an object and you want to turn it 45 degrees and then put it somewhere in 3D space, it means you have to rotate first to get your 45 degrees and then move it. Because if you move it first and then rotate, everything's happening around the origin of the system, so you'll end up with an object rotated somewhere out in the middle of who knows where, and it's not exactly what you were thinking it was going to do. Okay, so next we'll talk about transforming a vector. So how do you actually move a point around in space? How do you use a matrix with a vector? And so the way that we do that is it's the same concept as multiplying two matrices together, except that the other matrix just has one column, all right? So what we end up doing is say A, B, C, D times, you take the dot product of X, Y, Z, W, and that becomes your X component. You take the second row, E, F, G, H, and dot product with X, Y, Z, W, that becomes your next Y component. And that is how you transform your vector, say V prime, and V prime now represents V inside the space of M. So we talked about this idea of spaces and how they're perpendicular, right? And when we're thinking of Euclidean space, we're thinking, yeah, the x-axis goes on this direction, and the y-axis, say, goes up, and the z-axis goes in or out of the screen, depending on how you're looking at the problem. Okay, now if you wanted to get V back, you could just take the inverse of M and multiply it with V prime, and that gets your original vector out. Okay, so this stuff you can kind of undo if you need to. This is an important concept to remember for certain computer graphics algorithms, such as shadow mapping, camera transformations. So if you want to say, what does the scene look like if I put a camera in my scene looking towards the center or looking at a particular object? Okay, very important concept to understand. And then, of course, our identity matrix. So we mentioned it was just put ones in the diagonal, zeros everywhere else. Okay, so let's take a look at a few different matrices, all right? So the first one we'll take a look at is the translation matrix, okay? So you'll notice that in the rightmost column, we have Tx, Ty, and Tz, all right? So that means if we want to move a point around in 3D space, then we will just stick this Tx, Ty, and Tz. And if you think about when we talked about representing a vector or a point, we have the W component as 0 or 1. So 1 is a point, 0 is a vector. So if we were to multiply this matrix times a vector with a W of 0, if you look at this, right, we're looking at D, H, and L. You'll notice that D times W is 0. So we don't add that component. H times W is 0. We don't add that component. L times W is 0. We don't add that component. And finally, 1 times 0 is 0. So you'll notice that the translation has no effect on a vector. We can multiply, but if it is 1, then you'll just see how we just add that position. The point is going to move around in space, all right, if the W component is 1. So you can see the effect of setting W to 0 or 1 and that's called homogeneous notation. Okay, the next kind of matrix that's important is a scaling matrix. So if we want to make objects bigger or smaller, we would just set the components on the diagonal to represent how much do you want to scale in the x direction, how much do you want to scale in the y direction, how much do you want to scale in the z direction. And if you multiply this vector, you'll see that a times x gets saved, but b and c are zeros. So and d is also 0. So you'll just see that this is ax, fy, kz, and pw. You'll notice that we only make the x components bigger or the y component bigger, and so on. Then we have our different rotation matrices. Okay, this is probably the most important rotation matrix for you to remember. Okay, it's the most important one. The other ones look very similar to it, but this is the most important one. So with if you just kind of go to your trig, and you figure out, I want to plot a circle, and you have an angle theta, and you find out what's my x and what's my y, you know that your x component is just cosine theta, and your sine theta is your y component. So as you're drawing a circle, cosine theta is where you put your x coordinate, sine theta is where you put your y coordinate. And then over here, in the second column, we have that it's minus sine theta and cosine theta. This is technically 90 degrees orthogonal to cosine theta and sine theta, okay? And you will find that if you were to take the dot product of these two, then, for one, you should get 0 for that because they're linearly independent, and that's something you can show in the homework. Okay, if you take the cross product, you should technically get the z-axis. So you should get a 1 out for the z-axis. Okay, that's something you should work out and verify that that's how the case is. The more you work with these, the more familiar, the less strange they're going to become, and the better you are going to be working at using transformations in your 3D graphics programs. So the X rotation matrix, you'll notice basically that in the first column and first row, there's no change at all. So in this first one, you'll notice that in what we would think of the Z areas, there's no change. So if you're rotating around the Z axis, we expect there not to be a change in the Z coordinate. All right. Same for X. If you're rotating around the X axis, you don't expect to see a change in the X coordinate. And lastly, for Y, you don't expect to see a change in the Y coordinate as well. Okay, so they all more or less look the same as each other. And they all do basically the same thing, but for their respective axis. Now, let's say that you have a direction, though, that you'd like to rotate around. Okay, you don't just want to rotate around the X axis, or, because if you had, a spaceship flying through space, it's on its own rotation, right? So if you're going to rotate along the x-axis, it's not the same thing as your global XYZ axis. It's a different coordinate system. So if you needed to do something like that, you could also use a rotation matrix. And this, if you have XYZ, let's say that the norm is 1, in other words, it's a unit vector, and you have theta, and let's say we use C and S to represent cosine and the sine, then this is the matrix that you would use to construct that rotation matrix. We're going to see this again in a slightly different form when we talk about quaternions. Okay, but this is there's a way that you can look up how this is derived. All right, and I think you should do that. But to get an idea of how you can kind of create these more sophisticated matrices. Okay, so those are probably the most scaling, translation, rotation are probably the most useful matrices you'll use for moving objects around in 3D space. But what about projection? Okay, so the first kind of projection that you can do is called orthographic projection. So anybody seen a game or heard of the term isometric? You might have played an isometric game where there is no perspective, but you're looking at everything as if it's been shifted and tilted. So it's you can see it in 3 dimensions, but there's no foreshortening. In other words, objects further away from you don't become smaller. Objects closer to you don't become bigger. Everything's the same thing, but you got that 3D perspective. Or maybe an architectural drawing is done in a similar way. You kind of see the 3-dimensional aspect of it. Well, this is how you accomplish that. Okay. So this is kind of an ortho matrix, and this is used for those kinds of operations. The next is a perspective matrix. So this is, we're interested in doing a camera. And let's just say that we have we know the field of view, and let's just say we're going to pick on the Y direction. You can do it in the X direction, but let's just say we're doing the Y direction. In other words, let's just say you know that the camera has a 45-degree field of view going from top to bottom. Okay. So in order to do this one, we need to calculate the cotangent. And we take the cotangent of the field of view Y divided by 2, and we use that to calculate F. And then we have the aspect ratio, right? So maybe this is like one of those classic widescreen films, 2.35 to 1 or something like that, where you have a really wide angle of view for a movie film. Okay, so you need your aspect ratio, and then so you can see how your X and Y we scale those, and then Z looks different though. And this is where we're using this is going to be useful for an algorithm called Z buffer, which we'll talk about not today, probably next week. And we have to do some special calculations for determining how far back can the objects be and how close can the objects be before we decide we're going to clip it. Okay. And clipping is just a way for us to not have to have infinite depth, okay, precision inside of our depth buffer. Okay, and there's a formula to decide how many bits of precision that you lose. Okay, so there are a couple of common formats. So there's 16-bit depth buffers, which of course doing integer math, that means you have 65,535 unique values for Z. You could have 24-bit depth, bits of depth. Okay, so now you have like 24 million values for Z. Or you could do floating point, just save the actual representation of the Z value. But what ends up happening is if you pick values that are too far and too near, then you lose a lot of precision in your depth buffer. So for example, if I were to say objects can be as close as like, let's just say meters, right? So I'm going to say we're not going to clip objects that I'm 1 centimeter away from or that are 1,000 meters away from me. We won't clip objects in that range. Well, in effect, you lose almost 20 bits of precision here. And it's like you took your 24-bit Z buffer and now you only have like 11 bits. It's not very good. But if you were to maybe pick a more sensible thing, like, well, how about 10 centimeters away from me and 100 meters away from me? That might be more sensible. And you'll see that, we have quickly gathered or recovered a lot of our depth back. Okay, so when we're talking about perspective matrices, we're going to have to think about the depth buffer. So this is just a location. Well, this is where I'm just putting the math here just so we can kind of see the effect that this has on what's going to end up happening later. Okay, so moving through space. All right. So we all, if you're doing work in a 3D modeler and you're working at the object level, the object has its own pivot point. In other words, all the points that belong to that object are centered around this pivot point. Okay, they're not kind of represented in global 3D space. They're all locally centered. They're all, they combine everything together. So we need to be able to move from this local space to the global space or the world space. In other words, if I'm modeling all these different chairs, right, I don't want to model them as if that's exactly where they're going to be in 3D space. I model them locally, and then I can say, okay, let's transform it so that we have all the blue chairs in these positions and all the yellow chairs in these positions. Okay, so we would need a matrix to move those objects from object space, local space, into world space. And then once we've done that, we need to be able to view those objects. All right. So in order for me to view them, we need another we need another transformation to move those objects from world space into view space or camera space. Okay, and then on top of that, as we looked at earlier at the beginning of today, we had to move objects from the 3D space that they were in and divide by Z to project them onto a 2D plane so we can see them on our screen. Okay, so they can actually exist for us. Okay, so we have to move from a variety of spaces, all the way from object space to world space to camera space or view space to projective space to window. We're kind of going back and forth through different coordinate systems. Any questions so far? Okay. All right. And so as I mentioned, we typically use a matrix for these. Sometimes we don't use a matrix for object space because object space is kind of already, you don't need to move from like non-object space to object space. We just say this is the XYZ position. Okay, so one way of thinking about the matrix then is to treat each column as essentially the X, Y, and Z axis. Okay, so we might say the U axis represents the X direction, the V axis, the second column is the Y direction, and the third one is the Z direction. We'll just call it UVW. And then T is the position of the coordinate frame. Okay. And this is also another thing where we have to stick to, if we're using a left-handed rule, right-handed rule. Okay. If we were to pick one or the other, then our matrices would, when we concatenate them, then the order goes left to right and not right to left. Okay. So we're putting our feet on one side of the line and saying, okay, this is how we're going to understand it. Okay. And the reason I say this is because we have not yet talked about the view matrix, okay, which would be the last thing we talk today. But let's see how this works out, okay? Assuming this is the x-axis, y-axis, z-axis, and the actual location of the center. So if you were to look at an identity matrix, you would say, oh yeah, that makes sense because 1, 0, 0, 0, that's the x-axis, 0, 1, 0, 0 is the y-axis, 0, 0, 1, 0 is the z-axis, and 0, 0, 0 is the origin. Okay, so this makes perfect sense when you're talking about the global space. Okay, now if you want to prove it, you could take a look at a z-axis rotation of 26 degrees. And the reason I picked that is because you get a different value for the x's and a different value for the y's, and you know on paper what those angles look like. So this will allow you to kind of prove to yourself that the columns are exactly what that represents. Okay, so if we're transforming a vector with this idea that the matrices are following this pattern, and we looked at the rotation and the scaling and the translation, and we can see that they all kind of have this pattern to them. We'll just talk about rotation and translation. So we can see over here that we're basically doing a rotation to the X, Y, and Z, and then we're just adding on the translation. So we basically are saying we're moving it into a new space and then we're rotating it. Okay. And then, what would happen if we had introduced scaling? Well, then we might get some, it might change things on us a little bit. So scaling is a little bit of a, you have to just kind of watch what you're doing with scaling because it could cause your matrix suddenly to not be orthogonal anymore. Okay, so in world space. So generally speaking, this is where everything resides, and you give every object a world matrix, and then you can move another object into another space with the inverse matrix. And we're going to look at this for the camera. So if you know where the camera is located in world space, then you can take the inverse of that matrix. And if you notice that if I were to multiply the inverse matrix with the original matrix, I get the identity matrix. In other words, the camera is now at the origin. Everything else then is in the view of the camera, like where it should be in relationship to each other. Okay, and so this is the last matrix I want to show you is called a look-at matrix. Okay, and when you look at the documentation for this particular matrix, you'll notice that it's the product of these two matrices. So for one, we have the I coordinate. So where is the I located in 3D space? And then we have this rotation here, which we come up with a rotation. Oops. Sensitive there. We come up with a rotation by first saying, okay, we have the center, this is what we want to look at. And we subtract that from the eye. So now we have a vector looking from where the camera is located to the object we want to look at. We have the up vector, which says what direction is up pointing. And we can do some cross products here to make sure that they're all pointing at right angles to each other. Okay. And so, but when we look at this matrix here, we see these row columns here. Like we just basically said here, column vectors. See, we have this one axis, the U axis, the D axis. So if we look at this one and we see that these are arranged in columns, and then why are we subtracting the I position? This should clue us on that something is not a normal matrix. And that's because it's an inverse matrix. Okay. So when you look at this particular matrix, it could be confusing, but that's because what it's doing is first it's moving you to the I coordinates, and then it's rotating you around. Okay. And this is how you basically use a camera inside of a 3D scene. All right. Okay. So, don't think we have time to talk about projection. All right. But what I want you to do is play with the transformations for this weekend's homework. So whatever 3D engine that you guys chose to use, start looking at the transform. So if you're using Unity, right, the transform is like a big part of how the workflow works inside that 3D engine. Okay. Unreal, I think, has something similar, but look at the math routines that they give you and play around with the vectors and the matrices and so on. Okay. And I would encourage everybody to use the Discord channel to talk about what you guys are learning. Because chances are, if you guys are all learning together, then I think that's better than everybody learning completely separately. So use the Discord channel. And I keep an eye on the Discord channel so I can answer questions, and then everybody gets the benefit. It's like raising your hand outside of class. And everybody gets the benefit of seeing an answer for the questions you're having, because chances are this stuff is confusing. The first time you kind of play around with these, I hope I gave you a taste that they're all just kind of weird. The way that the math works is just weird, but it works out. And I think it's one of the fascinating parts of 3D graphics to begin with, is just the way that you can learn how math just makes reality work the way it does. All right, it's pretty fantastic. Okay, so we're out of time today, so it's 5 o'clock. So thank you, everybody. And if you have any questions, come see me after class. So thank you very much.